So here we are. It is Thursday, December 3rd, 2020. We are continuing with section 5.3, conditional probability and independence. We're going to get to independence in next week. The general, multiplication rule, and tree diagrams are the things we're going to look at today. All right. So first, we have the general multiplication rule. And this is the probability that events A and B are both occur can be found using the general multiplication rule. This rule is right here. P of A and B is equal to P of A intersect B. Okay, so we're using that new notation. And that's equal to the probability of A times the probability of B given A. So this is where probability B given A is the conditional probability that event B occurs given that event A has already occurred. All right? And this is not actually a new formula. This is just a reworking of our conditional probability rule. Okay, so if we recall from last class, the conditional probability rule is probability of B given A is equal to probability of B and A divided by probability of A. If I manipulate this equation, multiply each side by the probability of A, the probability of A cancels from the right-hand side, and we're left with this. Probability of A times probability of B given A is the probability of B and A. Now, notice this says probability of A and B. This is probability B of A. Probability of A and B is the same as the probability of B and A. And just because A and B or B and A is what's said doesn't change the probability in this for and statements. Doesn't change. Okay? So this is just a reworking of our conditional probability rule. When we rework it, we get the general multiplication rule. Any questions so far? Does anyone need a moment to write anything down? So let's do an example. All right. Here we have the Pew Internet and American Life Project find that 93% of teenagers ages 12 to 17 use the internet. 55% of all 19s have posted a profile on a social networking site. So, before I get to the problem, what are the known probabilities based on the context? And I'm going to say using the internet, call that event A, posting a profile, call that event B. So, 93% of teenagers use the internet. So the probability a teenager uses the internet is 93%. And 55% of online teens, so 55% of the 93%. So given a teenager uses the internet, 55% of them posted a profile. So that is probability of B given A equals 55%. Okay, so these are the two known probabilities based on the context provided. Is there any questions on how I came to those two probabilities? Okay. So then the question is, find the probability that a randomly selected teen uses the internet and has posted a profile. Right? So this is asking me to find the probability A and Norbert, shush. Nobody cares, Norbert. Sorry, guys. So, probability of A and B. Thanks for doing an and statement. Well, based on what we just learned, right, that new general multiplication rule, this should be equal to the probability of A on probability of B given A. Which we already have those numbers, right? Man, crazy how that worked out. Right, so the probability of A is 0.93. When you're doing the multiplication, it's easier just to convert these to decimals. It works in your calculator much better. Times 0.55. And if I'm remembering correctly from earlier today, this should be 0.5115. Those of you who are playing along at home, if you can double check my math, that would be awesome. I'll check it right now too. Yes, I'm correct. Ah, always nice. All right, so the probability that a randomly selected team uses the internet and has posted a profile is 0.5115, or about 51.15%. Or we could say it's approximately 51%, if we're asked to round to the nearest whole percentage. All right. Any questions on this example? All right. Does anyone need a moment to write anything down from this example? So that leads us to our tree diagrams. Right? Tree diagrams help us apply the general multiplication rule while creating a sample space that models the chance process that involves a sequence of events. So in general, tree diagram is going to look something like this. So we have some start point. Right? Maybe we're selecting from a sample of people, or something happens and it triggers a sequence of events, right? Depends on the context. So we have this start point, and let's just say there's two options. I'm just doing this in general. Let's say option 1 and option 2. And just for the sake of the example, let's say that there's a 60% chance option one happens, which leaves a 40% chance that option 2 happens. All right. Each step, or each part of the sequence that branches off of a single event has to add up to 100%. Hence 0.6 and 0.4. When we add those, we get 1. All right. Now let's say for the next stage here, there's 2 more choices. And let's just say it goes to a yes or a no type of thing. Right? And maybe if they chose option 1, they have an 80% chance of saying yes. Probably no is 20%. But if they choose option 2, they're at a 35% for a yes and a 65% for a no. This is what our tree diagram can look like. The more options, the more branches, right, the more it can spread out. Just depends on the context. We'll look at a couple examples after this. But in general, this is what a tree diagram does, and it allows us to very easily see the general multiplication, right? So, any questions so far? And again, anyone need a moment to write or draw anything from this slide? All right, here is our example. So Mr. Mosley hits the snooze bar on his alarm clock on 60% of school days. If he doesn't hit the snooze bar, there is a 0.9 probability that he makes it to class on time. However, if he hits the snooze bar, there is only a 0.7 probability that he makes it to class on time. On a randomly chosen day, what is the probability that Mr. Mosley is late for class? All right. So we have a couple different events going on. We have a sequence of things, right? It all starts when my alarm goes off. All right, so we can have that be the start. We have the alarm. And from the alarm, there's two options. Right? I'm either going to hit the snooze button or I'm going to wake up. Right? And I have 60% chance of hitting the snooze button, which goes to 0.6 as a decimal, meaning I have a 0.4 probability of waking up. So now, see, I have a 0.9 probability that I make it to class on time if I don't hit the snooze bar. So if I wake up, again, there's two options. I can be on time or I can be late. When I wake up, I have a 90% probability to be on time, which leaves a 0.1 probability, 10% chance of being late. If I hit snooze, I have the same two options. I can be on time or I can be late. When I hit snooze, I have a 70% chance or a 0.7 probability that I make it to class on time, which leaves a 30% chance or a 0.3 probability of being late. So this is my tree diagram for this scenario. Now that I have the tree diagram, I can answer the question, what is the probability that Mr. Mosley is late? Now there's two ways for me to be late, right? We'll follow it through the diagram, right? I can hit snooze and be late, or I can wake up on time and be late. So there's two paths to being late. So when I calculate the probability, I have to consider both paths. So we're finding what is the probability of being late. Now notice I'm not using a letter notation here for this. I'm just putting in the parentheses the thing that I'm trying to find the probability of. And that's totally fine. You can write it out without doing a letter. That's your choice. If you are going to use a letter, you need to state what the letter is. Right? So if I want to say late is L, then you have to say over here lit L be late for class. You would need to say that, then I could just use the letter L. If you do not say this, you cannot use a letter. In mathematics, we say that you must define your variables. You cannot just place them there and assume your reader knows what they are. Not doing that cost me many, many, many points on exams in college. Very frustrating. So now I remember. So, probability of being late is equal to the probability that I hit snooze and that I'm late plus the probability that I wake up and I'm late. And again, I'm using our little notation here, that kind of like upside down U. All right. So now this is where we get our new general multiplication rule. These two statements here, probability of snooze and late, based on the general multiplication rule, have to be equal to probability that I am, probability that I am late given that I hit snooze times probability that I hit snooze plus probability of wake and late. I have the probability that I was late given I woke up times probability that I wake up. Okay. This is the general multiplication rule at play now. Now, the probability that I am late, given that I hit snooze, is 0.3. Probability that I hit snooze, 0.6. Probability that I'm late given I woke up, 0.1. Times probability that I wake up, 0.4. So essentially what we do is we multiply our way through the sequence of events. 0.6 times 0.3, 0.4 times 0.1. Okay. So then 0.3 times 0.6 is 0.18 plus 0.1 times 0.4 is 0.04. And that leaves us with 0.22 as our probability, or 22%. Valentine, did you have a question?
Yeah, but right now I was thinking, and it was all right, but now my Wi-Fi just went shut down again, and just kicked me out of the call.
Well, thank you for getting back to the call. I appreciate it.
Yeah, I have to use my own Wi-Fi.
Ah.
My phone Wi-Fi to see this.
All right. Okay. So, probability that Mr. Mosley is late for class, 22%. Any questions on this example? Does anyone need another moment to write anything down? Now, same context, different question. Suppose Mr. Mosley is late for school. What is the probability that he hit the snooze bar that morning? So now, being late is given. And I want the probability that I hit snooze. I'm finding the probability that I hit snooze given I was late. Now, unfortunately, this is not what we've solved already. We don't have this number. The previous question used the probability of being late given that I hit snooze. All right? But we know how to set this up. This is our conditional probability rule now. So probability of hitting snooze given that I'm late is the same as the probability of snooze and late divided by probability of being late. Well, now we're in a good spot. We just solved the probability of being late at 0.22. The probability of hitting snooze and being late, we also have, right? If we go backwards, we have that right here, snooze and late, right? That's one we need. That's this one, or this number, 0.18. We actually already found that one. So we have 0.18 divided by 0.22. And that is 0.81818181818181, repeating forever. Oh, so we'll say 0.818 or 81.8%. And if they want you to round to the nearest whole percentage, we'd have approximately 82%. Okay. And there we are. Any questions on this step of the process? Do we need a moment to write anything down from this part? All right. So we have one more example. And this example is going to be very, very, very similar to the problem on the discussion board for today. Right? So I highly recommend paying attention to this example. Now, I don't have enough space to do this example here. Why we have this note here. This example is going to be worked out in OneNote, and it will be posted into the class resources for today. So we are going to jump over to OneNote. All right, so here we are. So the Kaiser Family Foundation recently released a study about the influence of media in the lives of young people aged 8 to 18. In the study, 17% of the youth were classified as light media users. 62% were classified as moderate media users. 21% they're heavy media users. Of the light users who responded, so given someone was a light media user, 74% described their grades as good, while only 68% of the moderate users described their grades as good, and 52% of the heavy users described their grades as good. Suppose that we selected one young person at random. Part 1. Part A, draw a tree diagram to represent the situation. Right, let's do that. So here's A. So our starting point is selecting a young person, right? So we have our young person that will be chosen. And those young people, there's 3 options. They will be a light media user, a moderate media user, or a heavy media user. Right? We have the 3 options. All right, 17% goes along with light, so 0.17. 62% was moderate, 0.62. And 21% were heavy, 0.21. The next part of the sequence here, the next option, is whether they classified their grades as good or bad. Let's go green. Right, so there's 2 branches coming off of each of these items. Right, we can have good or bad. And for the light users, given that someone is a light media user, there's a 74% chance that they describe their grades as good, so we get 0.74 for good, leaving 0.26 for bad. For moderate, we have 68% of good grades, 0.68, leaving 0.32 for bad. And lastly, for heavy, we get 0.52 for good, which remains with 0.48 for bad. So now we've filled out all the information we possibly can. We have our sequence of events. Our tree diagram is complete. Now we can start answering questions. Before I do part B, do you have any questions about how I created and constructed the tree diagram? So, part B, you need to find the probability that this person describes his or her grades as good. Right? So we're finding the probability of good. Once again, there are multiple routes in getting there. Right? We go with a light user. That's one way there. Moderate. Another way. And heavy. In this case, we're going to be adding up the probabilities of these 3 paths to get our solution. So we have the probability of good equals probability of light and good plus probability of moderate and good plus probability of heavy and good. So we just add them up, do multiplication. Right? Based on our general multiplication rule, we know that we just add the probabilities in the sequence. So we get 0.17 times 0.74 plus 0.62 times 0.68 plus 0.21 times 0.52. Right? which then goes to our handy dandy calculator once again. We get 0.1258 plus 0.4216 plus 0.1092. And ultimately, we add these bad boys all up. And we get 0.6566. Right? So the probability of selecting someone who describes their grades as good is 0.6566, or 65.66%, or approximately 66%. Any questions on how I calculated this? So then let's do part C. Part C saying, given that this person describes his or her grades as good, we have that word given, so good is the given part. What is the probability that he or she is a heavy user of media? Right, we're going with heavy as the part we're trying to find. So this question wants us to find the probability of heavy given they describe their grades as good. So we set this up. We have probability of heavy given good. Based on our conditional probability rule, this needs to be equal to the probability of heavy and good divided by probability of good. Well, that's super convenient because we have those numbers. Okay. Probability of heavy and good, right there, which is right here and right here. And probability of being good, well, that's the one we just found. So we set it up. We get 0.1092 divided by 0.6566. Right? And we get a number in the calculator. 0.1663, approximately. A little bit more to that decimal. We can also write that as 16.63%, or approximately 17%. Again, be careful. Read what the question wants you to provide. Does it want an approximation? Does it want a whole decimal and not a decimal with decimal percentage with decimals and things like that? So that's why I'm giving you the different representations. But yeah. What can I clarify? So then, last thing. If we go ahead and go into the weeks module, go to our using the general multiplication rule and tree diagrams discussion board for today. Here's our context. Here's our problem. A computer company makes desktop and laptop computers at factories in 3 states, California, Texas, and New York. California factory produces 40% of the company's company's computers. The Texas factory makes 25%, and New York makes 35% of the computers made in California. So given the computers are made in California, 75% are laptops, implying that 25% are desktops. Of those made in Texas and New York, 70% and 50% respectively are laptops. So the 70% goes with Texas, the 50% goes with New York. And again, you can use the known percentage to figure out the percentage of desktop computers produced. All computers are first shipped to a distribution center in Missouri before being sent out to stores. Suppose we select a computer at random from the distribution center. Construct a tree diagram to represent the situation. Same as what we just did in our previous example. You're going to have a start point. There's going to be 3 branches. Each of those 3 branches has 2 branches. Find the probability of the computer is a laptop. Again, you're going to follow your branches through, use your general multiplication rule, and determine the probability of getting a laptop. And then 3, given that a laptop is selected, what is the probability it was made in California? Very similar again to part C in our previous example. All right, you're going to use that general probability rule. And again, I suggest doing this on paper and then uploading a picture of your work. If you're having issues uploading a picture, just email me the picture. That works too.